My name is Mohammed Layiq Sediqi, the father of Holophase, and in this part of episode 5, we finally roll up our sleeves and use the idea we have been circling around. One hidden rhythm, three faces, time, space, and motion. If you remember where we are in the story, is in Taqtar episode 3 Bat, we said, only what can be read as phi on a clean window counts as real. In episode 4, we gently dethroned energy as the substance of reality and turned it into a summary of deeper patterns. In Toward episode 5, part 1, we walked through thousands of years of human struggle with time, space, and motion. In the part 2, we introduced the core idea of dimensional expression, time, space, and motion as three readouts of one underlying phase pattern. Now, in part 3, we do something crucial. We show you how this one rhythm, three faces idea actually appears in real experiments, not as poetry, but as practice. And we show you how to test it, how to attack it, how to look for cracks. Because Holophase is not asking for your belief, it is asking for your best attempts to break it. The one, try unity in plain language. Let's give our central idea a simple name. Try unity. In any clean experiment, one and the same pattern of phi simultaneously gives you a time readout, a space readout, and a motion readout. In other words, whenever you think you are measuring just time or just distance or just speed, you are actually reading different aspects of the same underlying phase pattern. Holophase claims this is not just sometimes true or conveniently true, but universally true. Wherever physics is well behaved, there is one underlying turning pattern, Bechai. Its change in time gives what you call frequency or tick rate, your sense of time. Its change across space gives what you call wavelength or pattern size, your sense of distance and geometry. The wave features of this pattern drift gives what you call velocity, your sense of motion. The bold claim is, you never need three independent primitive ingredients, time, space, motion, to describe a physical situation. You always can and should describe them as three readouts of one phi, that is triunity. Now we are going to test it in the lab, step by step, using very concrete pictures. Number 2, the laser, the mirror, and the three faces of one pattern. Let's walk into a very simple imaginary lab together. On the table you see, laser, pointing at a half-silvered mirror, a beam splitter, two paths for the light, one straight, one that bounces off a movable mirror, and at the end, where the two beams meet again, a dirt screen with bright and dark stripes, an interference pattern. You've probably seen a drawing like this, the classic interferometer. Now, stand with me at the screen and let's play a game. We will pretend we are experimentalists who never heard of space-time diagrams, never wrote an equation in our life, but we are extremely good at watching patterns. 2.1. Space from the pattern. First, freeze. The experiment in time. The laser is on, the mirrors are fixed, nothing is moving. On the screen you see bright and dark bands. Move your finger along the screen and you can measure how far apart the bright bands are. That distance between two bright stripes is a spatial readout of the underlying pattern. You don't see our fill itself. You see where the peaks of phi's interference land. If you change the path length of one arm, you move the mirror a little, the bands shift. From how much you had to move the mirror to shift the pattern by one stripe, you can infer the wavelengths of the light, which is just a way of saying how rapidly the underlying phase changes in space. So here from interference fringes, you get a by distance scale. The pattern gives you space, Zux 2.2. Time from the same pattern. Now keep your eye on one single point. On the screen, say a spot where it is bright right now. If you very gently wiggle one of the mirrors in time, say on a small speaker that makes it oscillate back and forth, that spot on the screen will flicker bright, dim, bright, dim. If you record how fast it flickers, you get a frequency. You can call that how many bright dark cycles per second. That is time readout. Notice, we did not bring in a new thing called time from outside. We observed how the same interference pattern changed as the mirror moved, and we interpreted the rate of that change as a timing signal. Here, from the flicker rate, you get a clock. The pattern gives you time. 2.3. Motion from the same pattern. Now watch how the bright stripes themselves move and across the screen when the mirror wobbles more strongly. Instead of one point flickering, you might see the whole pattern slide left and right like shadows moving on a wall. If you track how fast a particular bright stripe travels across the screen, say how long it takes to cross a certain number of centimeters, you get a churn speed pattern, distance per unit of the flicker time we just defined. This is a button motion readout, built purely from the pattern. So from one and the same underlying phase pattern of the light in one and the same experiment, you got a spatial scale, how far fringes are apart, a temporal scale, how fast brightness at a point oscillates, and a velocity, how fast fringes slide across the screen. Time, space, motion, all from the same underlying phenomenon. That is tri-unity in practice. We did not add three independent things. We read three aspects of one thing. Dethroned. 3. A tri-unity test you could actually run. Let's turn that simple picture into a test of Holophase. Imagine three teams using the same interferometer. Team time only cares about how fast one spot flickers. They build a clock out of that flicker. Team space only cares about how far apart the stripes are. They build a ruler out of that spacing. Team motion only cares about how fast one stripe moves across the screen when the mirror wobbles. They build a speedometer. Now we let them work independently for a while. Each team reports, we've defined our own second, we've defined our own meter, we've defined our own meter per second. Holophase makes a very strong claim. If all three are reading the same underlying phi pattern, their definitions must fit together. That means the meters per second that team motion infers from stripe motion must match the ratio between the meters from team space's stripe spacing and the seconds from team time's flicker rate. If they put their definitions together and they do not match within the known experimental uncertainty, then one of two things must be true. One, they have not properly accounted for how they are reading phi, a technical mistake. Or two, the idea that there is one underlying phase pattern giving all three observables is wrong in that setup. This gives us a tri-unity gate. Tri-unity gate. From one coherent experiment, build a clock, a ruler, and a speedometer, all from the same phase-based signals. Check if they are mutually consistent. If they are not, and you've ruled out technical errors, Holophase's tri-unity picture fails in that window. That is falsifiability baked right into the heart of the dimensional idea. Actually is nice. 4. Radar, catching speeders with phi. Let's leave the laser table and step out onto a highway. A police officer points a radar gun at a car. She squeezes the trigger. A tiny burst of microwaves flies out, hits the car, and reflects back. Inside the radar gun, something very interesting happens. It compares the phase of the outgoing wave with the phase of the incoming wave. If the car is moving towards the gun, the reflected wave comes back slightly shifted in frequency, a higher pitch. If the car is moving away, the pitch is lower. That shift is called the Knight's Doppler effect. But we don't need the name. What matters is that motion is read as a change in how quickly the phase cycles. From that shift, the radar gun computes a speed now, but notice what's going on. The time information comes from how fast the internal oscillator in the radar cycles. The space information, how far the wave front travels, is tied to the wave phase builds up as the wave moves through space. The motion information is extracted from the difference in phase between outgoing and incoming waves. Once again, one kind of pattern, an oscillating field with phase, gives all three: time, distance, and velocity. Holophase says this is not a coincidence of engineering. This is reality quietly revealing that dimensional information comes from how phi behaves. Here is a simple thought test that attacks Holophase. Could someone, in principle, build a radar-like device that measures speed without relying on any oscillation, any repeating pattern, any phase difference at all. If they could, and if that method could be made as precise and fundamental as phase-based radar, it would seriously wound the claim that motion is just how phase features move. But every real, high-precision speed measurement we know, radar, LiDAR, Doppler, satellite tracking, is built on oscillations and phase shifts. That does not prove holophase is right, but it is exactly what holophase predicts you should find in a phi-based universe. 5. Navigation. Where you are is a phase relation. Now let's go into your pocket and look at your phone. When your phone does navigation, it is not asking the universe for your absolute address. It is listening to a choir of satellites, each broadcasting an insanely regular ticking pattern, atomic clocks in orbit. What does your phone actually receive? It receives a sequence of pulses, each with a precise phase tag. The pulses from different satellites arrive with different delays. Those delays are nothing but phase differences between where the satellites think they are in their cycles and where your phone finds them. Then your phone does a clever bit of geometry. Given these phase differences to multiple known sources, where in space must I be and how fast must I be moving so that all these delays make sense at once? Out of phase differences in time, it reconstructs space, your latitude, longitude, and altitude, and motion, your speed and direction of travel. Again, one kind of raw data, phi relations between clocks, gives you all three dimensions. Holophase looks at GPS and says, this is what a phi-based universe must look like when it builds a navigation system. Your coordinates are not primitive, they are a convenient label for a consistent set of phase relations. So here is a tri-unity test in navigation language. If you mess with the phase patterns, change the timing signals in a controlled way, the reported time, position, and velocity must all shift together in a consistent bundle. If you try to shift time without touching the underlying phase, or to shift position without consistent shifts in phase relations, the system falls apart. In other words, you cannot tug at time, space, or motion independently in a GPS system. You tug at fine and all three move together. Holophase claims that this is not a special property of GPS, but a preview of how all precise physics works under the hood. There are 6 windows, coherence, and when tri-unity fails on purpose, now a very important subtlety in episode 3, we introduce the idea of a window, a finite patch of the world where the phase pattern is coherent enough to read, the noise is under control, and we can make precise, reproducible measurements. Tri-unity only applies cleanly inside and such windows. What happens when you open a window where the pattern is a mess? The light is incoherent. The waves have random phases. The signals are drowned in noise. Then, interference fringes blur out. Radar returns become fuzzy. GPS signals are lost. You can't build good clocks, rulers, or speedometers from scrambled phase. Time, space, and motion seem to break down together. Holophase says this is also a test. In a phi-based universe, wherever phase coherence breaks, all 3 dimensional readouts should deteriorate in linked ways. You should not find a situation where you can read time with insane precision. But all attempts to read space and motion from the same window collapse for no good reason, or vice versa. So we can phrase another falsification pattern: coherence gate. In any window where interference effects prove that phase coherence is high, time, space, and motion readouts must all be sharply definable and mutually consistent. In windows where interference proves phase is scrambled, all 3 must degrade together. If experiments show phase coherent systems with broken dimensional consistency or vice versa, the holophase picture has a serious problem. Notice how Dipole falsifiability is being baked into the logic laws of dimensional expression. We are not just saying everything is pretty waves. We are saying the quality of your dimensional concepts must track the quality of your phase information. That is a claim you can check. Larissa, 7. Tri-unity as a compression test. Let's step back and look at what tri-unity really does conceptually. Think of normal physics as storing 3 files. A file for how time behaves, a file for how space is structured, and a file for how motion works. Those files must be consistent. But in standard thinking, they are conceptually independent. You can tweak one without necessarily tweaking the others, as long as you keep the equations compatible. Holophase makes a stronger, more risky demand. There is only one underlying file, phi. The time-space motion files you are used to are all views generated from it. And here is the big payoff. If that is true, then the world is more compressed than we thought. Why does that matter scientifically? Because compression gives you extra checks. Equals. Imagine you have three separate descriptions, time, space, motion, that you wrote down independently, but one underlying pattern that claims to generate all three at once. Then you can use the underlying pattern to predict relationships between the three that were not obvious before, and use those relationships as tests. If reality passes those extra consistency tests, your compressed description looks more plausible. If it fails even one of them, the compression story is wrong. Holophase is essentially saying, let me compress three pillars of physics into one generator, phi. Then let me hand you a long list of the triunity consistency checks that must hold if that compression is truly how nature works. The examples we've discussed, interferometry, radar, navigation, are introductory hints of this. Each is a place where one type of physical setup gives you time, space, and motion data. Holophase says those data must fit into one Fashai description. Experiments can then be designed to stress that demand. Process 8. How to attack triunity and why I want you to. Let's be very explicit now. If you want to kill this dimensional expression idea, here are some concrete research-level directions, which we will later express more formally with equations and gates. 1. Build the triple measurement trap. Design an experiment where you measure time intervals using some process. A. You measure distances using some process. B. You measure velocities using some process. C. All three are as phase-based and precise as you can make them. Then test. Can one consistent phase pattern, FEHI, explain all three sets of data? Or do you need to treat time or space or motion as independent ingredients that cannot be squeezed into a single phi story? 2. Look for orphan dimensions. Search for a phenomenon where you can define a very precise time standard with no corresponding precise spatial or motion readout from the same system. Or you can define precise spatial structure, but time and motion become intrinsically fuzzy in ways that cannot be blamed on noise or decoherence. If such an orphan dimension is truly fundamental, not just a technical limitation, it would clash with Holophase's insistence that all dimensions co-emerge from the same phase data. 3. Beat phase-based standards with non-phase standards. Try to design a time standard not based on cyclic behavior, a distance standard not based on wave propagation or phase comparisons, a speed standard not based on periodic signals or their shifts, and show that these beat all phase-based standards in principle, not just in practice. Holophase predicts that as you push towards ultimate precision, you are forced back into phase language. If you can escape that, triunity is seriously weakened. 4. Find a physical law that needs independent time. Identify a robust, well-tested law of nature that cannot be rephrased in terms of how phi changes, without smuggling an independent notion of time into phi itself. In other words, show that no matter how cleverly you describe phi, you still need to bolt on an extra time variable that is not reducible to phase change. That would break the time from phi story. Holophase is not shy about this. This is not believe in a pretty theory. This is, here is the knife. Here are the places you can cut. If it collapses, good, the universe taught us something. That's 9, where we go next. In part 2, we built the intuitive picture. One rhythm, time, space, motion as 3 ways of reading it. In this part 3, we showed how that idea already appears in real experiments, interferometers, radar, navigation, framed triunity gates, and coherence gates as falsification tools, ways to test whether time, space, and motion really do co-emerge from phi in a given window. Emphasized that Every precise dimension measurement we actually use in practice is phase-based, exactly as Holophase predicts. In the remaining parts of episode 5, we will move closer to the formal side, still in simple language, show how the familiar structures of relativity and wave physics are nothing but refined stories about the dimensional expression of phi, and prepare the ground for where things get even more stunning. When we connect this dimensional story to forces, mass, curvature, and eventually to information and meaning. But before we go there, I want you to carry a very simple personal test with you. Whenever you see a clock ticking, a ruler being used, a car's speedometer, a wave on a string, a map on your phone updating as you move, whisper to yourself, is this really time, space, and motion I am seeing? Or is it one invisible rhythm showing three different faces at once? Holophase says it is the second. The rest of this episode and this project is our attempt to prove it and to give you, the listener, everything you need to decide for yourself.